Hi, everyone. Good afternoon. Welcome to today's Emerging Technology webinar series. Today's topic is a discussion with LIFT's CTO on aligning with DoD priorities. My name is Mary Ellen Doran. I'm the Vice President of Emerging Technology for AGMA. This meeting is being taped, so for those of you on the live event, please put your questions right into the chat. For those of you listening on demand, please send any questions to me at Doran, D-O-R-A-N, @agma.org, and I'll work to get answers for you. This webinar series has been made possible by generous donations through our members. Special thanks today to Liebherr, Vector Companies, Star SU, and Gleason. Thank you. Today's presenter is Noel Mack. Noel implements new technology focus areas to ensure alignment with Department of Defense priorities, directs large scope complex projects and programs, leads LIFT member involvement in technology projects, and serves as a mentor to LIFT's technical and engineering staff. Noel brings over 35 years of experience in engineering and design to LIFT. Noel, we welcome you and look forward to this presentation.
Well, thank you. And so, Noel Mack, CTO for LIFT. I'm going to talk a little bit about how a Manufacturing Innovation Institute accelerates material and manufacturing process development. So first, as we get going, I'd like to talk a little bit about LIFT. So we're a Manufacturing Innovation Institute. We focus on advanced materials, manufacturing processes, systems engineering, and talent development. We're a not-for-profit, public-private partnership set up by the government to accelerate technologies. We operate at the center of a powerful triad linking government, industry, and academia. So LIFT was originally formed in 2014 and operates under the guidance of the Department of Defense. Due to the success of the MIIs, the number has grown over the years. Currently, there exist 14 unique MIIs. When I say unique, it's because we all are independent and all have separate areas of focus. While LIFT focuses on advanced materials, others, like say AFOA, focus on advanced fabrics, ARM on robotics, NextFlex on flexible electronics, and so on. But key to this conversation today is that LIFT focuses on all advanced materials. So we convene industry, academia, and government. So this is a snapshot of some of the 340 members of the LIFT ecosystem. Industry on the left, academia in the center, and government on the right. So why do we need a National Advanced Materials Manufacturing Innovation Institute? Because literally everything is materials. The room you're in, the car you drove today, everything. It has been studied that an improved materials infrastructure could have a $270 billion positive impact on our US economy. Materials are also of critical importance to the Department of Defense because they not only allow our warfighters to achieve their missions, but better materials can better protect them so they can come back home safely. Now let's talk about how LIFT is the right organization to work on and to solve these materials challenges. So as a public-private partnership and accelerator, and important that we're an accelerator, not an incubator, we work in this MRL 4 through 7 space. So if you look at the manufacturing readiness level space, 1, 2, 3 really in the research and academia, 8, 9, 10 is mainstream, commercial and industrial partners. This gap in the middle, this MRL 4 through 7, is often known as the valley of death, connecting the good ideas which have legs into commercialization. So as stated in the prior slide, LIFT is the technology accelerator. Thus, we tend to spend our time in this MRL 4 through 7, known as Valley of Death, but we look at it differently. We see this as the Sea of Opportunity. This snapshot is the DoD's view of us in those two humps in the middle, from MRL high 3s into early 8s. So we work on rapidly transitioning technologies across this space. We lower the risk of technology adoption, scale new advanced materials and manufacturing processes into commercialization. We provide access to an advanced manufacturing sandbox within our facility. This makes us an ideal partner for building a resilient materials supply chain. So as the National Advanced Manufacturing Innovation Institute, We operate a 100,000 square feet facility at our headquarters here in downtown Detroit with over $55 million of manufacturing equipment. This facility sets us apart from other MIIs in that we are not limited to our members' manufacturing capabilities. We stand up our own equipment to study and solve today's materials challenges. So we manage and execute roughly 30 tech projects at any given time, involving large OEMs and small manufacturers along the way, and with our government partners. We create and distribute talent development programs to over 30 states nationally, allowing returning servicemen and women to quickly and smoothly re-enter the workforce. And we're growing, expanding operations into Puerto Rico and shortly into Florida. All of this drives a significant ROI back to the taxpayer, but most importantly and proudly, it bolsters our national security. So we achieve all of this through our technology and talent programs. Our focus today, though, is on a technology program known as Leading Innovations for Tomorrow. So this is how we accelerate technologies. There's a rather busy slide, so I'll break it down in the subsequent sections. These pillars around accelerating technologies are starting on the left with digital engineering, moving to the advanced materials design, coupled with a manufacturing process to understand that both materials choice and manufacturing process results in a part or system that is fit for purpose. How do we know it's fit for purpose? Through the next pillar, verification and validation, ensuring the digital models, materials choice, and manufacturing processes are correct, and closing the loop with the validation. Then we work with our industry partners and the government to scale these technologies up and move towards commercialization. So I'd like to take a few moments to describe our approach to materials development. Material development takes a long time and is costly due to the extensive testing and validation that's required. We're typically stuck in the build and break era. As a result, new materials are failing to keep pace with the more rapid design innovations. Yet new materials hold the key to new and exciting innovations. There's a path forward, integrating material modeling into systems modeling. This can enable us to break the pattern. Not only can it evaluate materials that cannot be tested, it can also reduce development time and cost, improve quality, and increase manufacturing efficiency. This really yields significant economic and strategic benefit. By stopping failed programs early, accelerating time to market, we found over 35% acceleration factor. We can increase the overall efficiency by over 70%. We can reduce the cost of development and manufacturing, or both. It helps to build a robust material supply chain, and the overall economic benefit, we believe, is close to $300 billion annually. As an example, the supply chain for metal additive manufacturing, or AM feedstocks, such as powders and wires, presents several challenges. These impact the scalability, cost-effectiveness, and reliability of this emerging manufacturing technology. Here are some of the challenges. First, material availability and standardization. Not least of all is lack of standards. Jump back. Feedstock production challenges. So in this case, it's really important to understand the complex manufacturing processes. Producing high quality metal powders involves an energy intensive process like gas or plasma atomization, which requires precise control. We need to consider powder morphology and the limited recycling through the process. High costs, it's expensive raw materials and low economies of scales in most parts. Supply chain vulnerabilities, we're currently highly dependent on specialized suppliers and a lot of geopolitical and market risks. Quality assurance, variability in feedstock quality, testing certification comes into play. Sustainability concerns, energy-intensive processes, end-of-life management need to be considered. And then integration with other manufacturing systems, lack of compatibility, and all the logistics and storage issues that go along with metal powders that are sensitive to environmental factors, moisture contamination, etc., not to mention handling, packaging, and storage solutions. So, as I mentioned, we strongly focused on material development, particularly in extreme environment applications. We do a lot of independent work in this area to help accelerate the state of the art. We're building out an end-to-end ecosystem to support material development from start to finish. It really rests on these three top pillars, which is design, build, and test. So the objective here is to design, build, and test the part, the material, and the process simultaneously. So we're very active in digital engineering. Unfortunately, we're also standing up, however, we're also standing up capacity to deliver metal feedstocks to support these new material discoveries, as well as the capability to produce custom ceramics and CMCs. That's the next pillars over. And finally, we engaged in the development of a new state-of-the-art extreme environment test facility in the state of Michigan. That's the fourth pillar, overheat. And again, everything we do is to accelerate technology development so it can move into commercialization. So let's talk a bit about what we're doing first in the digital space. So I spoke about significant economic opportunities await us. What we really need to do here is integrate material modeling with systems modeling. However, there's a bunch of challenges that exist. Today, we've got discrete silos between materials development, manufacturing processes, and structural applications. In many cases, these are different departments even in most of the companies we work with. As an example, with additive manufacturing, the material and the part being created at the same time, they're inextricably linked and they influence each other. So it's very difficult to design them in silos. So by creating this materials-focused, model-based systems engineering approach, we can aggregate knowledge across these silos. So really link the materials, the application together, creating an environment that combines both the digital and the physical. So that's a lot to consider. We're talking about linking the atomic to the nano, to the micro, to the macro scale from end to end. Today, there are lots of applications to help you along the way to solve these parts of the process, but there's no singular software in existence that addresses the varied needs of the material community across the full spectrum. Each does create a digital twin of its respective physical partner. However, there's not much connectivity between these twins. So today, with no common interface linking all these disparate tools, and if there is, oftentimes they don't speak the same language, so spinning the thread still requires manual intervention. Essentially, some codes speak German, some codes speak English, and some might speak Spanish, but we need to do the translation from one to the next. So we're really left with a collection of digital twins and fragments of digital threads that require expert knowledge to navigate and synthesize. So what we know as MIDAS, which is our Materials-Informed Digital Acceleration Suite, is a digital platform that supports both material design and manufacturing process development. It facilitates and automates data translation between the codes, creating a robust digital thread across multiple digital twins. It automates the process, giving rise to accelerated development, and supports a digital validation and qualification strategy. So it allows users to understand if the materials are fit for purpose as a function of the chemistry and process. We can study process parameter development and perform optimization of design or process, or both simultaneously, and perform the virtual qualification. You could call us the Rumpelstiltskin of ICME. So we're really spinning the straw into a digital golden thread that connects these disparate systems, allowing one to create tomorrow's next material breakthrough. So at the same time, once you have a new material, it still requires physical trials and validation. So we also need to accelerate this process. We're currently standing up equipment to manufacture metal additive feedstocks across the full periodic table. We'll then take those materials and, leveraging equipment on our shop floor, produce parts for testing. We're not limiting ourselves to metals only. We are also highly engaged with the next generation ceramics and CMCs and other extreme materials. Similarly, we are not limiting ourselves to additive manufacturing, but supporting a full array of traditional and novel manufacturing methods as well. So we're focused on technology acceleration. We're focusing on this center and small development scale volumes in novel materials. The Advanced Metallic Production and Processing Center will be capable of producing novel alloys across the periodic table, from steels to refractories, and will support the broadest AM process from powder bed fusion to DED friction stir, welding, cold spray, and others. We start at the beginning by melting alloys to your specs or designs of our own recipes, and then post-process these materials to deliver high-quality feedstocks in powder, wire, and rod form. This should support the broadest of AM processes. So, putting this in a different context, put this into a brewing context. Academia, research organizations working on flights and pint-sized batches. We're in the growler and keg quantity, and then industries producing truckloads. This capability fills the void between the two quite capable existing bookends and helps speed development of novel materials. Here's a snapshot of the type of equipment that we've built this differentiating capability around. From alloying in open air or under vacuum to mechanical milling with our tritter, we can then swage and wire draw or gas atomize to process powder, or spheroidize the milled powders to provide flow characteristics that we found to be necessary. Or create extrusions for rods for, say, friction stir additive or for the sake of extrudability. So a couple of words on each of these capabilities. Some of the specs on the melt cast capability. So this really goes from the reactives, the aluminums, tires, and zirconiums through the light elements, aluminums and magnesiums, through to the ferrous and other materials. We can run in two separate modes, either a hybrid hot crucible or an induction cold crucible mode with roughly 28 to 30 liter batches. We clearly talk about the volume because if we're working in the lights and the brights up to the some of the heavier materials, it's more important that we focus on the volume than the mass. But think of 500 pounds of steel is a typical batch size through this capability. On the tritter, here we're really intending this for the refractories that we can't put through the traditional alloying process. This is really crushing the particles together. Think of two different colored Play-Dohs and constantly melding them until they become one. Here, the particles that come out look more like cornflakes and need to be, in most cases, spheroidic in nature to flow through downstream processes. So in this case, we'll feed them through the spheroidizer to get spheroidic particles. On the atomizing side, can be run again in multiple modes, roughly 90 liter capacity for the screw feed or 60 odd for the tube feed. And then we can also run an induction hot wall crucible for a closed coupled operation, which is for non-reactive materials. This equipment that you see in the picture stands roughly 26 foot high, so pretty much fills the high bay to the ceiling. On the swaging and wire drawing, we typically start with a roughly 45 millimeter diameter rod. We'll swage that down to roughly 1/2 inch and then run that through a traditional bull blocks to as small as 0.6 millimeter diameter wires. If we think of one rod that has been cast, and we can cast up to 24 rods at a time, one rod that is cast, if we drawing that down to say 0.6 millimeter, that represents about a mile of wire. So through this capability, we can produce roughly 24 miles of wire from one batch through the melt cast process. Then, of course, to further evaluate these materials, we need to, in most cases, produce a part for testing. And here we have a host of other equipment in place, whether it's AM or traditional manufacturing. We've got equipment on hand to manufacture and then test. Some cool recent additions. Two of the most recent additions to our high bay is first ECS or FAST or SPS, depending on where you live in the world. So direct current sintering is the most common term that we use inside of our organization. Some people would call it field-assisted sintering technology, spark plasma sintering. Either way, this equipment is stood up, and here we're running at roughly 250 tons and just on 1,000 amps of current that we pass through this to get to max operating temperature of about 2,500 C. On the right is a more recent add, which is our plasma arc weld DED cell that we've stood up. This can run up to 8 wires simultaneously to either alloy on the fly or produce functionally graded structures. We can run this in an 8-wire, 4 or 2-wire mode and put down materials at up to almost 60 pounds per hour with a hot wire insert on the 2-wire feed. We can also run this with shielded gas or with a fully inert environment. So we literally flood the entire cell, purge it from the bottom up with argon, so we can run in a full inert environment if we need to. And if we're making alloys and the respective parts, we need to be able to test. So speaking of testing, we've got a comprehensive materials lab to ensure the final output meets the specs requested. And this ranges from traditional structural performance down to atomic level and power draw chemical analyses. To enhance our nation's capability and complete this digital thread, step back one, to enhance the capability and complete the digital thread, we're putting in a new hypersonic and extreme environment test facility as well. This will also be installed in Michigan. And this links the 3 capabilities together: design, build, and test, allowing us to complete the digital thread from start to finish to greatly accelerate the next generation material development. The jewel of the facility, of the test facility, is the hypersonic tunnel. This will get up to speeds of roughly Mach 8, stagnation pressures around 2500 psi, and temperatures in the 4000 Kelvin range. It'll be well positioned as one of the highest performing tunnels in the US for materials testing. It'll have operating test area of roughly 9 by 9, 9 inch by 9 inch exposed area, which positions it well for material development. It also has the ability to perform high strain rate and shock testing in the same facility. And this will be done with split Hopkins bar, Taylor and planar impact testing, along with light gas gun, which gets us to speeds of roughly Mach 23. Now, the planning of this facility is well underway, and the first equipment will be procured through this year, and commissioning is just around the corner. So, together with that, we obviously need the capabilities to do traditional materials testing, tensile fatigue, fracture toughness, and the ability to perform these tests at elevated temperatures, as well as unique testing for ablation, oxidation studies, which is common in most extreme environment cases. So, unless there are questions, I'll switch over to a few examples of how this framework has been exercised in several of our past projects. First example being the experimentally coupled hypersonic digital twin to scale materials. So here we've developed a unique alloy in the digital space, including the consideration of its performance attributes in a hypersonic environment. And we've tested it in the appropriate environment to confirm and correlate with the digital. So in the ICME space, so starting with the digital, starting in the ICME, here we've looked to collate and develop and mature the hypersonic relevant ICME models. We've modeled across the continuum, but continuum from geometry and microstructure through the process, capturing the properties and then predicting the performance. But in this case, I'm going to look at just the microstructure, 3D powder bed printing, and hypersonic performance simulations. So here you see the predicted microstructure evolution from the laser beam powder bed fusion process, as well as the evolution from the heat treatment history. So starting with microstructure of the actual laser beam powder bed fusion process, and then running that through the simulation of the heat treat process. The objective here is to identify the presence or hopefully lack of deleterious phases, and also to observe the grain growth. In this case, we use the phase field code to do the simulation. Here's an example of the macroscale output, where we've extracted the location-specific thermal histories and residual stresses. And then finally, on the right, we've simulated the hypersonic performance of these wall-mounted wedges. You'll see 2 distinctly different simulation results at the bottom. Both are from popular mainstream software codes. The first one I've redacted the name of, which is a density-based code. It's been extended for hypersonic speeds. specifically to account for non-equilibrium thermodynamics. And this is using arbitrary Euler-Lagrange solver. The second software that was used for the same simulation happens to be Cradle CFD, also density-based solver, and also an ALE solver. In subsequent slides, I'll show the importance of these two softwares and the interpretation of the results. So in this case, we actually purchased powder for this project because our capability was not yet commissioned. And first off, we evaluated the chemistry and the particle shape and size to ensure we had correlation with our simulation. We manufactured the test coupons with our EOS M290. So here's pictures at the bottom of the actual build plates as they've been built. You can see in this case, the geometries were not that exciting, being test coupons and wedges. We've done the post-build heat treatment with a modified ASTM standard, stress relieved parts, and then removed from the build plate using our YEDM. So we've then taken these samples and done the V&V. So on the V&V side of things, here's a snapshot of some of the physical test results overlaid over the simulation predictions. So if we look at the test results being the red dots on the screen, which in some cases are completely overlapped with blue dots. The blue dots are from the CFD code number 2. The orange dots are from CFD code number 1. So it's quite clear from this simulation that the two software packages are not predicting anything close to reality. This is valuable feedback, though, that we can now provide to the software companies. As you can imagine, most software companies don't have the luxury of elaborate materials test capabilities, especially in hypersonic environments, and also don't have really access to results that are needed to fine-tune these codes. So this, we believe, is a unique value that we can bring to our software partners in our ecosystem. Some of the graphs from the post-test are evaluated, and then we look at location-specific areas which we zoom into to actually understand what has happened, and looking at precipitate phases through our SEM with the EDS. So scaling this up, part of the commercialization of this capability, we're now standing up what we know as our heat capability. Heat stands for our hypersonic and extreme environmental test facility. Once this is done, we'll not only have the experimentally coupled hypersonic digital twin to scale material solutions, but we'll also have the entire capability from the digital, the CAD and chemistry, through the material production and processing feedstock, as well as the part build, all under one roof. So everything from soup to nuts finally be in one house, which we believe really helps to accelerate the process. So this is how the respective swim lanes of effort align with our tech pillars and build out on these differentiating capabilities. The second example I'm going to look at is from a program we knew as the materials characterization for additive manufacturing using ICME. So in this case, the ICME scope is to develop models with an emphasis on characterization of metallic materials used in additive 3D powder bed printing, as well as additive manufacturing using traditional gas metal welding or MIG. Here, the focus of the next couple of slides is really going to be on the gas metal additive manufacturing side, and not so much on the powder bed printing, because that was covered in the prior program. So in this case, our simulation focus is really on dilution modeling. Unfortunately, again, most of what we're looking at are not very exciting parts. We start typically with single track. In this case, it was nickel deposited on a steel plate, looking at measuring things like dilution. The objective here was to determine the extent of the material mixing and the dilution. And in this case, we use thermocalc, and then on the CFD side, using Flow 3D as the CFD code. Here at the bottom graphics, you can see the the weld beads as they are simulated, as well as some of the thermophysical properties on the right-hand side. So the second focus is on weld strategy. So here we're looking at simulating different weld strategies. Clearly you can weld these bands by going round and round, or you can weld them in a zigzag stitch pattern. And the objective here is to predict and compare thermal histories of the respective weld strategies, not just the thermal history of the bead we're laying down, but also the substrate, to ensure that we understand whether there's any propensity to crack through the heating and cooling cycles. So in those two small graphics, you can, I hope, see the animation of the simulation of those weld beads being put down in these respective models. So we then put this into the physical, and here you can see a snapshot of the inside of the cell that this was built on the top right graphic. Here we put down 1, 2, or 3 layers of nickel welds on this 4140 steel plate. We've got thermocouples on either side of the weld beads so we can understand the thermals. We also have a cooling channel underneath so we can control the cooling, and we like to cool below the steel martensite temperature between the successive beads, so we actually put a delay in the weld strategy. We run the metallography to evaluate the bead morphology and penetration, and then look at the microstructure and property changes to the steel substrate as well as the beads that we put down. So here we're looking at a large format gravity aligned metal system. So if you look at this graphic on the bottom right, this is a snapshot of the hybrid manufacturing WAM, our Y-arc additive cell. I'll talk in a few slides' time about how this is morphed from a MIG-based cell into a plasma arc cell, but I'll hold that for a couple of moments. This particular cell in the instance in this program was built on a Fronius CMT TPS 4000 with Fronius arc monitoring. We used 2 Phallic 6-axis robots, weld arc vision with dual wavelength and high-speed thermographic acquisition, so we can watch what's going on in the cell real time and then compare those back with the simulation. So we ran an extensive design of experiments to do the probabilistic modeling of all the input parameters, and then looked for candidate parameter sets to do subsequent builds. Obviously, all the in situ and post-build data is compared with the ICME models and then correlated, and then in cases fine-tune the predictions to more closely represent reality. So here's some of the reality. So if we look at some of the discrepancies between the predicted weld beads and the measured weld beads, in most cases, the simulated beads are smaller. So looking to understand those so we can feed that information back to the software companies again to improve the software capabilities and giving them opportunities to build high fidelity models for future usages. In the bottom, we've got the model capabilities are not available in some cases. So we're feeding back information that can be used to build those out. So here we're looking at test results again versus simulations. Test results as well as literature. So not as well studied in literature as we'd hoped. You can see the 3 different literature curves. You can see the purple curve, which is the simulation curve, and then some of the test results in the respective colors. If we look at the graphic at the top left, that's a top view of the build block. So essentially, if you look at the top right of the screen, you can see the block that we've built. So we built out that block with a continuous welding process, and then excised samples in the longitudinal and transverse, as well as the diagonal of that block, and then put those through the respective tensile and other property testings. So this is where we learned about some of the shortcomings of MIG and have now upgraded the cell to a plasma arc weld cell. So this is the cell that I spoke about previously, and this has been built out with the 8, 4, and 2 wire deposition heads. In this case, we've actually coupled the two Fanuc robots. So instead of running as 2 6-axes, we're running as 1 12. And you can imagine with a 12-axis system, as well as up to 8 wires being fed and the control of the plasma, there's some extensive programming that goes on behind the scenes to make all of this happen. So again, as we put this program and the respective swim lanes across the tech pillars, this is how it lines up from the digital through the materials, studying the manufacturing processes, the verification, the validation, and then the opportunities to scale up and commercialize. The last program I'm going to look at is something slightly different. So in this case, we're actually looking at the standing up of a pilot line to build what we know as electrochemical separator plates. This pilot line will run at pilot rates of roughly 15,000 units annually, and that pilot production should kick off in May of this year. So again, starting the simulation. From the simulation perspective, we're looking at the hydroforming simulations of the rubber bladder to form these foils, determining the pressures that we need to fill the tool with the foil to form the plates. In this case, the steel, using a steel blank rubber bladder with a pressure load, and then the die is simulated as a rigid body, and we're using abacus in this case. We obviously need the capacity to fill the void, and in this case, I don't know why we left the last graphic off here, but we found we need roughly 28 KSI in the hydroforming system to be able to fill the void, or to be able to fill the tool, should I say. So here's putting it into reality, taking this graphitically coded 316 materials in the cutting fixture. In this case, the graphic shows a non-formed plate. The plate form itself is controlled, so I won't show you the actual plate form, but here's showing a blank in the system. We need to form them. We need to laser cut, mark, laser weld, apply the silicon sealant bead, and then run the end-of-line pressure test. So in the graphic on the right, you see us working on tuning and adjusting silicon dispensing nozzles to be able to put the silicon seal down as well. You said graphitically coded 316, and then the silicon seal. So here's looking at the manufacturing line design. So in the digital space, again, looking at the value stream mapping, and then the production layout, and then running that production layout in the process simulate software, so actually simulating that entire cell so we can do the calculations and the production calculations in the virtual space before procuring equipment. So as I said previously, we're doing the metal forming, inspection, cutting, welding, robotic application of the sealant, curing the sealant in the oven, and then end-of-line testing. Here you see a picture of the interlocking press, and the radii are as tight as 0.1 millimeters in this case. So really important that we get the forming right to know that we have the performance characteristics that we need. So this is the 1,000-ton interlocking press that is sitting just adjacent to the cell that you'd seen in the prior slide. The graphic on the right, that's been shaded out so that the sensitive information is removed, but essentially what would be hidden behind those two red circles are some of the tight tolerances that we need to hold through this process. Here's just looking at the silicon bead going down with an XY table, really using a cosmetic applicator with an extrusion nozzle, and then a mastic regulator, and then a trigger valve to actuate it. On the VNV side, we've done the relevant SPC studies to know that we can form plates and not just form one, not just form a couple of hundred, but get to full production rate. So we ran X number of plates through the system, did the appropriate measurements, and tuned in the forming simulation or forming parameters to match the simulation to be able to get to the capabilities that we need. Final slide here on this one is looking at the actual cell. So this is the process simulate running. You can see the worker running around the cell, moving from one piece of equipment to the next, finishing one process, running it over. And this is where we would do our calculations to understand the operating efficiency and parts per hour, parts per day, and do the upfront calculations so that when we do, or before we bought the equipment, we knew that it would actually be fit for purpose. So again, putting those in the respective pillars, so design, build, test, or digital engineering in the materials and manufacturing process focus, verification, validation, and then through to scale up and commercialization. So just putting these back into those respective swim lanes. Finally, in conclusion, all of this pulls together what we call ADAM, or Accelerated Development of Advanced Materials, the philosophy that we're adopting. So it's really a comprehensive ecosystem, scalable and replicable. We're looking at the development, our focus is really on the development, scale up, and commercial transition of novel materials, processes, and parts. And then ADAM is not being built in a vacuum. It's being built with insight and collaboration with our government, industry, and academic partners up and down the value chain. So finally, if you want to know more, contact myself or Christine Longroy, our Senior Director of Ecosystem, who helps us keep all of the plates spinning in the system. So that's enough of me talking, and I'll hand over and open to questions.
Thanks so much, Noel. There's so much there, and I have so many questions. But I want to start by saying you talked at the beginning of the slide about the fact that you have 300 partners. Could you just spend a minute talking to our folks about how they can become partners with Lyft, and do they just talk to Christine? Could you elaborate a little?
So I'd like to say just talk to Christine. The company is a lot bigger than just Christine and I. We're roughly 60 people in total, roughly 30 people in the tech team. But as an entry point, yes, get a hold of Christine. How we work across the ecosystem, essentially, as I said earlier, we're here to accelerate technologies. So not to incubate, but to accelerate. These technologies often reside in the small and mid-sized companies and need to be accelerated into sometimes the larger industrial companies. So if we look at our member structure, the very top tier, which we know is our platinum tier, that's the big players, Siemens, Kearney, Hexagon. As we come down, we've got the next tier down, which is our gold members. Gold are typically let's say the bigger players, the Primes, the Lockheeds, the Raytheons, the Northrop Grummans. We've got the silvers, which is typically in the tiered supply space. And then what we see as the, I hate to call it the lower tier, but the sort of entry tier, which is often the mom and pop shop. So in many cases, there's some really good ideas, some really novel technologies that are residing in some of the small and mid-sized companies. And working through our programmatic efforts, we can scale those technologies, link them up with big players, scale them across the valley of death, follow through the sea of opportunities we like to see it, and help those technologies find their way into mainstream high volume production. I'd call out one small example, small company Bond. Bond, I think, is a 5-man company down in Indiana, had a really cool novel technology in refill friction stir spot welding. They were actually on a webinar that we're running, and Boeing was listening in. Afterwards, one of the tech fellows from Boeing called us up and said, "I really need to talk to those people. We'd like to find a way to insert that technologies into our mainstream airframe production." So that on the back of that, there was a small lift-funded program which helped to accelerate that and prove the viability, prove the possibility in airframe manufacture.
I really appreciate that you spent a little bit of time on the accelerator piece of Lyft as opposed to the incubators piece, because that is who you are and what you're about. So that's fantastic. Thanks so much. I'd like now to open it up. We don't have a question in the chat. If someone would like to unmute themselves and ask a question, please do so at this time. I'm hoping we don't have people talk over each other. If you have a question for Noel and you don't want to speak to the entire group, please send that to me directly at Doran, DORAN, @agma.org, and I will connect you with Noel for your direct questions. At the conclusion of this presentation, you'll receive this slide deck with Christine's information. Is Christine still on the call? I know she was. If you just would like to introduce yourself.
Hi, everybody. Yes. Good afternoon, everybody. I'm Christine Longray with Lyft. I figure I'd just say hi. So yes, happy to talk with anybody to help integrate them into Lyft. So welcome. Thanks, everybody.
Thanks, Christine. Without any further questions, Noel, this was a fantastic presentation. Lyft is doing a lot. I'm very excited to see 3 years from now, 5 years from now, all of this technology out in the open and accelerated and helping the nation as a whole. So thank you very much for all that you do. And thank you everyone for attending today. Our next presentation, we have webinars every first Wednesday of the month at 1 p.m. Our next presentation is February 5th. We'll be talking with Igor Ortiz of I'm sorry, I'm gonna get this wrong. Erkun and Aaron Isaacson of the Gear Research Institute, who will discuss ring gear repaired with Divar material by laser power direct energy deposition. Thanks, everyone, and have a great rest of your day.
Thank you.
Have a great day, everyone.